Hi students, good morning everybody. In today's video we are going to discuss about energy in simple harmonic oscillation. Any particle executing simple harmonic oscillation will have two types of energy, potential energy and kinetic energy. You all know that for simple harmonic motion, the force and the displacement are related by Hooke's law, which is given as F vector is equal to minus K into R vector. Force is a vector quantity in three dimensions. Force has three components, but the force in the above equation is a conservative force field. You all know that a conservative force field can be derived from a scalar function which has only one component. So in one dimension we can write this expression as F is equal to minus Kx. Already we have discussed in the fourth chapter the work done by a conservative force field is independent of path. So for this case the potential energy U can be calculated using the following expression. The expression is F is equal to minus du by dx. So comparing this equation 10.63 and 10.64, we can write minus du by dx is equal to minus kx, or du is equal to kx into dx. This is the small change in the potential energy of a simple harmonic oscillator. Now using this expression we can write the work done by the force F during a small displacement dx is stored in the body as potential energy. So from du we can write u of x is equal to integration of kx dx. Instead of x here it is substituted as x dash, because when you apply the limits you have to take the limit from 0 to x. So instead of x we are using x dash because it is a dummy variable. So u of x is equal to integration from 0 to x kx dash dx dash, which is equal to half. When you integrate this, you will get it as x dash square by 2. So as a result, the above equation will become equal to half kx dash square from 0 to x. After substituting the upper limit and the lower limit for x dash, you will get u of x is equal to half kx square. And we all know that the value of the force constant is given by K is equal to m omega square. We have already studied about in the starting of this chapter that the value of K is equal to m omega square, where m represents the mass of the particle and omega represents the angular frequency of the particle. Taking this expression for K and substituting it in this equation, we will get u of x is equal to half m omega square x square, where omega is the natural frequency of the oscillating system. For a particle executing simple harmonic motion, we have already studied that the equation for displacement is x is equal to a sine omega t, where a represents the amplitude of the particle. So x square becomes a square sine square omega t. Substituting the value of x square in this equation of for ux, you will get u of t is equal to half m a omega square a square sine square omega t. Why we have written here as u of t is because here it is a function of time, so only you are writing it as u of t. So this expression u of t is equal to half m omega square a square sine square omega t represents the potential energy of the particle executing simple harmonic motion. We can represent this equation in the form of graph by taking time along x-axis and the potential energy of along y-axis. You will get a curve like this. So this graph represents the graph which represents the graph for potential energy of a simple harmonic oscillator. Now let us see the expression for kinetic energy. Yeah. The kinetic energy Ke is equal to half m Vx square. Vx is nothing but dx by dt. So kinetic energy is equal to half m dx by dt the whole square. We all know that for a simple harmonic oscillation, the displacement x is equal to a sine omega t. Therefore, velocity v is equal to dx by dt. So, what we have to do? We have to differentiate this equation with respect to time. When you differentiate this equation x with respect to time, we will get vx is equal to a omega cos omega t, which is equal to a omega. Instead of cos omega t, I can write root of 1 minus sine square omega t, which is equal to a omega into root of 1 minus x by a the whole square. How we know that? From this expression sine omega t is equal to x by a. So only we are getting v of x is equal to a omega root of 1 minus x by a the whole square. And after simplification, we will get v of x, that is velocity of the particle executing simple harmonic motion, is equal to omega root of a square minus x square. Substituting this expression in the kinetic energy, we will get Ka is equal to half m omega square into a square minus x square. If you substitute the value of x is equal to a sine omega t and the simplification, we will get finally kinetic energy is equal to half m omega square a square cos square omega t. This can be represented by the graph. So this graph represents the variation of kinetic energy with time. So we have all learned about the expression for kinetic energy and potential energy of a particle executing simple harmonic motion. So what is the expression for the total energy here? The total energy is the sum of kinetic energy and potential energy. E is equal to Ke plus U, which is equal to half m omega square into a square minus x square plus half m omega square x square. So if you expand this equation, you will can able to find that half m omega square x square minus half m omega square x square will get cancelled. So finally we will get E is equal to half m omega square a square. In this expression, m is a constant, omega is a constant, a is a constant. So the total energy is a constant, or in other words I can write E is equal to half m omega square a square sine square omega t plus half m omega square a square cos square omega t, which is equal to half m omega square a square into sine square omega t plus cos square omega t. Using trigonometric identity, you all know that sine square omega t plus cos square omega t is equal to 1. So the above equation will turn out to be E is equal to half m omega square a square. So E is equal to half m omega square a square is equal to constant, which gives the law of conservation of total energy. This graph represents the graph for total energy here. That is this graph shown in violet color. Color gives you the potential energy. The graph shown in green color shows you kinetic energy. In this case, at any position, the total energy always remains constant. When you simplify this equation and rewrite this equation, the amplitude A of the simple harmonic oscillator can be expressed as A is equal to root of 2E by m omega square. You know m omega square is equal to force constant K. So A is equal to root of 2E by K. the graph shows so this diagram shows that in any case the potential in the total energy of the system remains constant. That is, if you consider the spring mass system which is undergoing simple harmonic oscillation, when the spring mass system is at the position A, the energy is both wholly potential, because at the position A the displacement is maximum, the velocity is zero, so the energy is totally potential. But at the position B, that is at the mean at the position B in between, it has both kinetic energy and potential energy, so that the total energy is this. At the position C, the energy is wholly kinetic, because this is the mean position. Position A represents the extreme position and position C represents the mean position. Position B represents any position in between extreme position and the mean position. So at the mean position, as the body is having zero displacement and maximum velocity, it will have maximum kinetic energy, so the energy is wholly kinetic, and the total energy is wholly kinetic. Like this, in each and every case it can be shown that the total energy of the system always remains constant. Now let us see about types of oscillations. The first type of oscillation is called free oscillation. When any oscillator, what do you mean by oscillator? Any body which is allowed to undergo simple harmonic motion is, or simple harmonic oscillation is called as an oscillator. When an oscillator is allowed to oscillate by displacing its position from a equilibrium position, it oscillates with the frequency which is equal to the natural frequency of the oscillator. Then such an oscillation or vibration is known as free oscillation or free vibration. In this case, amplitude, frequency and energy of the vibrating object remains constant. This is a very important one, and examples are vibration of a tuning fork, vibration of a stretched string, oscillations of a simple pendulum, and oscillations of a spring mass system are all examples for free oscillation. You should always remember that in free oscillations, the body oscillates with its own natural frequency. The next point is, in this case, amplitude, frequency and energy of the oscillating body always remains constant. Next, damped oscillations. In the previous case, we have assumed that the oscillations of a body remains constant and also the total energy. But in reality, in real practice, real case, that when a body oscillates in a medium, due to the presence of the friction and the air resistance, what will happen? The amplitude of the oscillation does not remain constant. It decreases as time progresses. So when the amplitude decreases, automatically the energy of the oscillator also decreases. So here there will be no constancy in amplitude and constancy in energy, and there will be some loss of energy. The energy lost is absorbed by the surrounding medium. Then in this case, the body will not continue its oscillations and it will come to rest after some time, and such oscillations are called damped oscillations. In other words, I can say, if an oscillator moves in a resistive medium, its amplitude goes on decreasing, and so the energy of the oscillator is used to do work against the resistive medium. The motion of the oscillator is said to be damped, and in this case, the resistive force or the damping force is proportional to the velocity of the oscillator. So if you take time along x-axis and amplitude along y-axis, relaxes. Initially the amplitude is maximum. Because of the resistive force, the amplitude gradually decreases exponentially. Finally the amplitude becomes zero. Examples: the oscillations of a simple pendulum oscillating in air and the pendulum oscillating inside an oil-filled container. Electromagnetic oscillations in a tank circuit. You will study about the tank circuit in 12th standard. Then oscillations in a deadbeat and ballistic galvanometer. The next type of oscillation is a maintained oscillation. While the child is playing in a swing, you all know that after some time the oscillations of the swing will stop after a few cycles. This is due to the damping. Due to air resistance, the oscillations will come to rest. To avoid damping, what we will do, we will give a small push to the swing so that the oscillations in the swing will maintain constant. So by pushing, what we are doing, we are supplying energy from an external source. So as a result of supplying energy from an external source, the amplitude of the oscillations are made constant. Such oscillations are called as maintained oscillations or maintained vibrations. Example: the vibration of a tuning fork getting energy from a battery or from an external power supply. The next type is forced oscillation. This is the fourth type of oscillation. Any oscillator which is driven by an external periodic agency to overcome the damping forces is known as a forced oscillator or driven oscillator, and such type of oscillations are called forced oscillation. In this type of oscillation, the body executing vibration initially vibrates with its own natural frequency, and due to the presence of the external periodic force, after some time the body vibrates with the frequency of the applied periodic force, and such vibrations are known as forced vibrations. Example: soundboards of a stringed instrument like veena, guitar, etc. The next one is resonance. It is a very important factor. Resonance is a special case of forced vibration. You all know that in a forced vibration we are applying external periodic force. So the external periodic force will have its own natural frequency and the body will have its own natural frequency. What do you mean by the term resonance? In the case of forced vibration, when the frequency of the external periodic force, the external periodic force can be called as the driving force, or it is called as driver, and the body is called as a driven. In the case of an forced vibration, if the frequency of the external periodic force matches or equals the natural frequency of the vibrating body, then the body will vibrate with a very great amplitude, large amplitude, and such a case of vibration is called as a resonance. Such a phenomena is known as resonance, and the corresponding vibrations are known as resonance vibrations. So resonance is a case in which the frequency of the driver and the frequency of the driven matches each other or equals each other, so that the oscillator will vibrate with the maximum amplitude. The energy of this oscillator will be maximum. Such type of oscillations are called resonance oscillations, or I can say the body will be oscillating with the resonance in such a case. Example: breaking of glass due to sound. The next one is the concept. This concept of resonance is very important, and it is used in tuning of stations or channels in either a radio or a television. You all know that while we are making use of television or radio, if you want to get a proper channel which we desire to see, we will use the tuning knob knob. So in such a tuning case, the frequency of our system, television system or radio system, matches with the frequency of the desired station which we want to hear. So in such a case, resonance occurs. So resonance is very important in the tuning circuit or tuning of radio and television. Another important application of resonance is when soldiers are marched or marching while they are crossing a bridge. Soldiers are not at all allowed to march on a bridge. Why the soldiers are not at all allowed to march on a bridge? Why when they are crossing a bridge? Because when the soldiers go on marching in a bridge, what will happen means the soldiers' footsteps will have a particular frequency and the bridge will have its own natural frequency. So while crossing a bridge, if the period of stepping on the ground by marching soldiers equals the natural frequency of the bridge, what will happen? Resonance will occur, and as a result of resonance, the bridge will vibrate with the maximum amplitude and it may collapse. So in order to avoid the collapsing of the bridge, soldiers are not at all allowed to march on a bridge while they are crossing a bridge. Okay, so thank you girls.